Okay, so next week in lessons, you are going to be moving on to a new topic and you're going to be doing the triple only content. So everything we've done so far has been the same as the combined students, but then next week we start the triple only content. And for paper one, there are 4 topics that are triple only. So I've made a separate booklet that you will be given at the beginning of Wednesday's lesson. In that booklet, I've only put the first 2 topics. I've put SC13 and SC14. I haven't done 15 or 16 yet. I'll do that after half term. SC13 is relatively short. It's on metals, and you will do it in just 1 week. So over 2 lessons, we're going to do SC13. It's relatively short. It's relatively straightforward. SC14 is a bit longer. It's a quantitative analysis and is an extension of the moles topic that you just did. So there's more calculations in SC14. So you'll do SC13 in 1 week, and then you'll do SC14, the longer topic, over 3 weeks. So you'll be given this booklet on Wednesday, and I've put exam questions into the booklet, and I've put the mark scheme so that when you're doing your work in class, you've got the mark schemes there to mark your work straight away. Also with the practice questions, any questions that I've written myself, I've also included all of the answers. So obviously the idea is not just to copy all of the answers to make it look like you've done the work. The idea is to do the work yourself, but then to mark it when you're done, to make sure that you're doing it correctly. If you're getting the wrong answers and you can't figure out why, please just message me on Teams and let me know. It's also very possible that I've made some mistakes with the answers, so if you do spot any, please do let me know. So as I said, the topic you're going to do next week is SC13. It's on the transition metals, alloys and corrosion. So because we're going back to look at metals, I thought I'd just do a little recap first of what we have learned about metals so far in the other chapters of the course. So before we go on to the new stuff, we'll just look at some of the old stuff. So we first came across metals when we looked at, I should be down here. We first came across metals when we looked at CC7, which was part of structure and bonding. And we saw that the structure of metals was giant metallic lattice. I'm just going to draw out the structure of a metal so you can see what I mean by this. Okay, so if I draw, for example, sodium, okay, so sodium is a metal. It's made up of sodium atoms, and because metals are solid at room temperature, I'm going to draw these sodium atoms arranged as if sodium was a solid. So sodium is a group 1 metal, meaning each of these sodium atoms would have 1 electron in their outer shell. And we know from looking at the reactivity of metals that metals want to lose electrons to get that full outer shell. So when you've got all of your sodium atoms with 1 electron in their outer shell, what they will do is they will lose their electrons. But if your sodium is not reacting with another element, there's nowhere for those electrons to go. So what happens is your sodium atom will lose the electron and become a positive ion. So I'm going to draw all of these atoms again, but with a positive charge now. And I'm not going to draw their electrons. They do lose their electrons, but because it's not reacting with another element, those electrons that I've drawn here have nowhere to go, and they stay within the structure of the metal, and they move around through the structure of the metal. So I'm drawing those electrons there as negative charges because electrons are negatively charged. And what you end up with is you end up with this repeating structure where you've got layers of positively charged ions stacked on top of each other, and you've got the delocalized electrons moving through the positive ions. Because you're not just doing this with 1 metal atom, you're doing this with billions. We say the structure is giant. Again, it's a metal, so we say it's giant metallic. And because you've got this repeating structure as it's a solid, we say it's a lattice, so giant metallic lattice. Holding the metal together is an electrostatic force of attraction. So anytime you've got something positive and something negative, we say the force between something positive and something negative is electrostatic. So we've got the electrostatic attraction, and it's between the positive ions, so right, BTW as between the positive ions and the negative delocalized electrons. Now we've come across the electrostatic attraction before, and we've seen that the electrostatic attraction is very strong. So when we looked at ionic bonding, we saw that there was a strong electrostatic attraction that was difficult to break, and that meant that ionic compounds had high melting points. It's exactly the same for metals. That electrostatic attraction is very strong. A lot of energy is required to break it, and that means that metals have high melting points and they are solid at room temperature. The other property we looked at is due to the delocalized electrons. Because they've got charged particles, electrons are charged, that are free to move, so delocalized means they move through the structure, that means that metals can conduct electricity. So we came across this in CC7. Metals have a giant metallic lattice, that is their structure, they have high melting points and they conduct electricity. In CC11, we looked at the extraction of metals. This is the topic that we've just done. So we looked at electrolysis, we looked at reduction by carbon, but we also looked at the reactivity of metals. And we saw that metals always lose electrons, which we just saw up here. And when they lose electrons, they always form positive ions. And we saw that the group 1 metals were more reactive than the group 2, and they were more reactive than group 3. And then we had zinc, iron and copper from our transition metals. And then at the end of our series, we had silver and gold, which were relatively unreactive. We looked at different reactions of these metals. We saw that only our most reactive metals could react with water, but our less reactive metals would react with acids. And we said that the group 1 metals are so reactive because they only have 1 electron to lose, and that's much easier than losing 3 electrons like the group 3 metals have to do. The last chapter that we came across that involved metals was CC13. We did this in year 9 and we looked specifically at the group 1 metals, which are called the alkali metals. The alkali metals are metals, okay, so they have this giant metallic lattice structure and they do conduct electricity. However, compared to other metals, they do have relatively low melting points, and that word relatively is really important. It means compared to other metals, the group 1 metals have lower melting points. They're still solid at room temperature, they still have much higher melting points than simple covalent molecules, but compared to other metals, the group 1 metals had low melting points, and they're also much softer than your typical metal. You can actually cut them with a knife. So in this new chapter, as I said, our focus is going to be on the transition metals. So here you've got your group 1, your alkali metals, your group 2 metals, you've got group 3 over here, but then most of the metals on your periodic table are actually part of the transition metals. We've already had a look at iron and zinc and copper and silver and gold in CC11, but we're going to look at the transition metals in general now in this chapter. So you don't actually need that much information on the transition metals, you just need to know their properties. And when we're talking about properties, you can divide properties into physical properties and chemical properties. So physical properties, you're talking about the appearance of the metal, how they taste, how they smell, also their melting, boiling points, and whether they conduct electricity. That all counts as a physical property. Chemical properties then specifically refer to how they react. So if we have a look at the typical physical properties of transition metals, they're all stuff you should be familiar with. They have high melting points. Again, we've just discussed why, because of that strong electrostatic attraction between the positive ions and the negative delocalized electrons. They have a high density. So density is calculated by mass divided by volume. So basically, if they have a lot of mass in a small space, then they will be considered to be dense and they will sink on water. If they're more dense than water, they sink on water. Malleable, you would have come across that word in year 7. It means they can be hammered into different shapes. That's a very useful property because we use metals, things like making cars. You have to hammer the metal into the shape of a car. Ductile means it can be drawn out into wires. Again, very useful property. Something like copper is used for electrical wires and you can draw it out into the shape of a wire. And again, good electrical conductors, we've talked about why, because they have delocalized electrons that can carry current. So they're the typical physical properties of your transition metals. In terms of chemical properties, we've seen that some of the transition metals are very unreactive, but for those that do, again, when they react, they're metals, they will lose electrons, they will form positive ions. But when they react and they form compounds, those compounds are typically coloured. So we've seen in one of the previous topics that copper sulfate, that would be an example of a compound of sulfur, and it's blue. It's a really nice blue colour. And that's typical of the transition metals, that when they react and they form compounds, those compounds have bright colours. Transition metals can also be used as catalysts. So we came across this word catalyst in year 9. Catalysts are used to increase the rate of a chemical reaction, and transition metals can be used. In a later topic on equilibrium, we will look at the use of iron, which is one of our transition metals, and how it's used to catalyze the production of ammonia. So the properties that I've gone through here, we've come across these properties already because they're just general properties of metals. So below I've just written that aluminium, which is in group 3, and then also your metals in group 1 and group 2, they share many of these properties because they are all metals. However, if you actually compare the density and the melting points of your group 1, 2 and 3 metals with your transition metals, you'll see that the transition metals have much higher melting points and densities. So sodium, as I said, sodium is group 1. So this is your group. Why are you doing this to me? Sodium is group 1, magnesium is group 2, aluminium is group 3, and if you compare the densities of those 3 metals to the density of the transition metals, you'll see the transition metals are much more dense. And by dense, I mean they've got a greater mass in a smaller volume, so they feel much heavier, even if you've only got a small amount of them. Also, if you look at melting points, we said sodium, it's group 1, it's an alkali metal. We said that they had relatively low melting points, and if you can compare, you can really see that. 98 degrees Celsius to turn sodium into liquid, 3,422 degrees Celsius to turn tungsten into a liquid. So your transition metals have much higher densities and melting points than your group 1, 2 or 3 metals. Again, these are just typical properties. There are always going to be exceptions. Mercury is a transition metal. It does have a high density, but it's got a low melting point of -39 degrees, and mercury is actually a liquid at room temperature. So yes, these are typical properties, but there will always be exceptions. On the next page, I've just gone through some worked examples. I mean, essentially you just need to know this content, but you do need to be able to apply it as well. So a typical example here, why is copper used to make electrical wires? So copper is a metal, it's got all of these properties, but you'd have to pick out the properties that are relevant to it being used in wires. So for example, copper is not used in electrical wires because of its high density. Okay? Copper is used in wires because it's good at conducting electricity. It's also ductile. So they're the 2 properties that copper possesses that are important for being good, for being used as an electrical wire. So they're the 2 properties I'm going to mention in my answer. Most of these examples here are totally self-explanatory. I'm not going to go through them all. This one, compounds of transition elements are used in paints and dyes. Why? Well, I said here that compounds of transition metals are usually coloured. You want a paint or dye to be colourful. That's why you're using transition metals in paints or dyes. At the end, copper and gold, they both conduct electricity. Why do you prefer copper when making electrical wires? Again, that's just more common sense than anything else. Gold is more expensive, so if you need to make wires, you're going to use the cheaper metal, you're going to make copper. So there's a couple of worked examples there on properties of transition metals for you to go through. I haven't included practice questions this time around. There's not a lot of content in this topic, so at the end of the booklet, you'll see all of the exam questions instead. So when you're going through the content, just read through it, maybe make yourself some notes, try and learn off the content, and then when you're familiar with it, you can move on to the exam questions, and the mark schemes are at the back. But that is all you need to know about the properties of transition metals, and just familiarize yourself with these kind of typical exam questions. The next thing we need to look at in terms of the transition metals is corrosion. We need to look at what corrosion is and how we protect against corrosion. So corrosion is when metals react with substances in the environment and they become weaker. And because they're becoming weaker over time, this will lead to the deterioration of the metal. The typical thing that they are going to react with in the environment is oxygen. So when they react with oxygen, this is called oxidation. Remember, we came across that word oxidation already. It's the addition of oxygen. Reduction is the opposite, it's the removal of oxygen. So if you've got a metal just sitting out in the open air, it will react with oxygen. We say it is oxidized, and when it reacts with oxygen, it becomes weaker. Your classic example of that is iron. Okay, if you leave iron out, it will react with oxygen and form iron oxide. So if you think of iron, that strong metal, when it reacts with oxygen and forms iron oxide is rust, that brown flaky powder, much weaker than the iron that you started with. So when they react with oxygen, when they're oxidized, they are becoming weaker, therefore we say they corrode. There are other elements that they can react with as well, but oxygen is the most common one that they will react with. Okay, and so yeah, iron gains oxygen, so it is oxidized. The more reactive the metal, the faster it will react with oxygen. So if you left something like sodium, a reactive group 1 metal, out in the open air, it is going to oxidize, react with oxygen, a lot quicker than iron, which will oxidize slowly over time. However, not all metals become weaker when they react with oxygen, and copper is a classic example of that. So the Statue of Liberty is actually made out of copper. And the outer layer of the copper that's exposed to the oxygen does react with oxygen, but it forms what we call a tarnish, which is a protective layer. And that protective layer prevents the rest of the copper that make up the Statue of Liberty from reacting with the oxygen. So the outer layer reacts with oxygen, forms a tarnish. That tarnish then protects all of the metal underneath. So yes, it's still reacting with oxygen, but it's not deteriorating over time because the tarnish prevents it from becoming weaker. So copper and aluminium are both examples of metals that can form a tarnish, and because they form a tarnish, they don't corrode. Yes, they still react with oxygen, but they don't become weaker. Remember, to corrode, you're becoming weaker. They're not becoming weaker because that tarnish protects them. And on the Statue of Liberty, it's the green layer. That's the tarnish. It protects all of the copper underneath. For metals that do corrode, you want to protect them from corrosion. Okay, so this is particularly important for metals that are used for structure. So if you were building a bridge out of a given metal, you don't want it to corrode, you don't want it to become weaker over time. So you need to protect these metals from corrosion. To protect them from corrosion, you want to protect them from oxygen. So there's a couple of things you can do. One, this is obviously not if you build something, but if you just want to protect the metal from oxygen, you can store in an unreactive atmosphere. So argon is a group 0 element. It's a noble gas. It's very, very unreactive. So instead of having the space above your metal filled with oxygen, you could remove the oxygen, fill it with argon or even nitrogen, and the metal won't react. We've seen something similar with the storage of alkali metals. You store them in oil. They're stored in oil, again, to protect them from oxygen and also to protect them from water. So that's in terms of storing them. If you actually want to use your metal for something and they have to be out in the open air, you can coat that metal with paint, plastic, oil or grease, and that can stop the metal underneath reacting with oxygen. If we look at iron in particular, because iron obviously the corrosion of iron has a specific name, and that is called rusting. So we use that word rusting specifically when we're talking about iron. It's not correct to say that copper rusts or aluminium rusts. That word is specifically used for iron and iron alone. However, steel is an alloy of iron. We're going to see that in the next video. So an alloy is just a mixture of a metal and something else. And steel is a mixture of iron and carbon. Because there is iron in steel, you can also say that steel rusts, but it's the iron that's the important element for rusting. It does require oxygen, but it also requires water. So you need both water and oxygen for iron to rust. So I've got an equation here, iron plus, iron, yes, there we go, iron plus oxygen plus water, and you get what we call hydrated iron oxide. So it's the iron and the oxygen giving you iron oxide, but the water is present as well, and you get hydrated iron oxide. So if you want to protect your iron from rusting, again, you can prevent iron reacting with oxygen by the same methods we outlined above. You can also protect it from water. To protect it from water, you can use what we call a desiccant powder, and that powder will absorb all the water vapor. You need oxygen and water to rust, so if you can protect the iron from either, you are going to prevent the iron from rusting. The other thing that you can do, is what's called sacrificial protection. And in this case, you take a more reactive metal. So there's lots of metals more reactive than iron. So group 1, group 2, group 3, and zinc, they're all more reactive than iron. And you attach that to the iron or the steel. Remember, steel contains iron. The more reactive metal is going to react with the oxygen instead of the iron, and that will protect the iron until all of that metal has corroded away. Typically, magnesium will be one that would be used. If you use a group 1 metal, they're so reactive that they react so quickly that they corrode really quickly, and then the iron is left to react. So you want something more reactive than iron, but not so reactive that it reacts instantly. So magnesium or zinc are typically used. They'll react with the oxygen instead, and that will protect the iron. So if we look at some examples of questions on this, okay, so what is rusting and what must be present for rusting to occur? So rusting is specifically the corrosion of iron or steel, and you need to have water and you need to have oxygen for it to occur. How can you prevent rusting? Okay, so 2 marks there. I've gone through a couple of different answers. Okay, you can say protect it from oxygen, you can say protect it from water, and you could give a different answer there for protecting it from oxygen. Protecting it from water, you're going to use a desiccant powder. Is sodium suitable for sacrificial protection? I mean, it says evaluate, so you need to give the pros and cons. I mean, essentially, yes, sodium is more reactive than iron, and that's the main criteria for being a sacrificial metal. So it is more reactive. It will preferentially react with oxygen and save the iron. However, it's so reactive, it will react really quickly and therefore is not particularly useful. You're better off using something like magnesium. Copper reacts with oxygen and forms copper oxide but does not corrode. So remember, corrosion, it's not just about reacting, it's about reacting and becoming weaker. The reason that copper doesn't become weaker is because it can form a tarnish, and that tarnish prevents the rest of the metal reacting, so it protects it from corrosion. That's the end of the worked examples. Again, there are lots of exam questions at the end with the mark scheme, so when you feel comfortable with the content, you can move on to the exam questions. I'm going to do one more video. In that video, I'm going to go through the last 2 sections, electroplating and alloys. It's more of the same, not a lot of content, just a couple of worked examples, and then you should be set to do all of the exam questions in your cover lessons next week.